What I want to do in this core session, I thought of doing it in one session, but the amount of things to be covered in case if I need to do it in slower pace, it may need two sessions, but it's worth spending time now before we get into the real processing of AI using different algorithms. We should see where do those AI algorithms run. Okay, our focus is to see AI algorithms running on IoT. Now, we need to also understand where exactly these algorithms are going to be run, what hardware support and memory support is required, so that you have a good understanding of where exactly your algorithms are going to be executed from, and you can appreciate very well. Apart from that, if you are aware where is it running and what are the limitations or what are the strengths of the platform, then you should be in a position to manipulate or fine tune your AI algorithms so that it runs faster and with a minimum number of cycles and you get a better performance. So always, whether you are writing a software or embedded software or even the AI algorithm for a particular hardware, if you know where exactly it is going to run and what is the environment is about, then you can always tweak your algorithms, the software that you write, so that it runs faster and gives you a better result. So that is the intent of introducing you to the hardware portion of the AI algorithms running. Okay, so let us see. To understand that, I'm sure all of you must have heard of it, heard of memory hierarchy. I also touched upon that in one of my lectures in this course. I thought I'll spend little more time to introduce you to the issues which are involved and how it is handled in GPUs, so that you can appreciate uh, how GPUs are used for AI algorithm on AI platforms. Okay, now let us just get to know about memory hierarchy. I'm sure all of you are aware. You know that CPUs are the brain of whatever executing. Finally, whether you are writing it in any language, as I told you in the Python course also, they all converted into some assembly instructions which are understandable by the CPUs, and they access that data which is required for them to operate on. So the instructions what the CPUs understand are the assembly instructions which need to be fetched by the CPU to execute it. So we need not only the code that is which is getting executed, also data to be available closer to the CPU so that they can manipulate it. Now, normally the reduced instruction set computing, okay, sorry, okay, reduced instruction set computing insists that the instructions are of single clock cycle. That means one assembly instruction always takes one single clock cycle to execute, so that you have much faster throughput in terms of number of execution of instructions per second, per clock second, per clock cycle. Apart from that, the RISC type of processors have the fixed width of the instruction. That means it will be either 32-bit or 64-bit. And then RISC also has, the architecture has more registers in them. More number of registers are more. That means they can manipulate the data by keeping them in the register itself, because the registers are the inside the CPU, which is much easier to access, so that is the most easily accessible storage area to the CPU, apart from the cache and memory and all that. So if you have more registers, you can manipulate more. So RISC processors are good in terms of having more registers. But one limitation with the RISC processor is they cannot do any memory operations. That means you cannot say add some memory location M1 and M2. Okay, you cannot add the contents of memory locations M1 and M2 and put it in the M3, another location. All the values need to be brought into the register to perform any arithmetic operation, either add or multiply, whatever you do, they need to be brought into registers. That means only two instructions which are accessing the memory: store and load. Load means it's writing into the memory. Store is, I'm sorry, this is storing. Storing is writing into the memory. Load means load from the memory to register. So only these instructions are memory related and all other instructions are all register related. That is the philosophy of RISC processor. And most of the time it was understood that the memory accesses are less frequent than the processing, and we can have, if you have more registers, we don't need to access the memory too often because we can accommodate them in the register. So we can perform all the operations within the registers maximum extent. So that RISC processors were the way to go, and then it has been followed in all the processors now. That is all for computing CPUs. But that is not true with our AI algorithms or the GPUs. The problem with AI or the GPU in particular, graphics processing, is the amount of data involved is huge. Suppose if you are processing a 4K picture, each pixel is going to occupy, as I told you, for each color, and then the resolution, it may be 32-bit or maybe more. That means so many pixels have to be processed simultaneously. So even in graphics, what we need is more amount of data to be manipulated. So the normal processing of RISC type of thing will not work because we want every element to be in the registers to be operated. So that architecture does not suit well for graphics processing. So they brought in another kind of an architecture, which is a graphics processing unit, wherein you have the memory which is closer to the ALU, and we have not only single ALU, we have multiple ALUs. The reason being because all the processing is the similar processing you need to do for all the pixels. So we have more data, okay, multiple data, but similar instructions to be operated on those things. Suppose if you want to enhance the color, or if you want to transform the image or rotate the image, you need to perform the same rotation for all the pixel elements in the graphics. That means you are doing the same operation on multiple data. Keep in mind, I will tell you something more about the architecture which is meant for graphics processing. So one thing is we need more data to be processed in the graphics area. In fact, that is also true with AI. That's why AI uses GPUs for the processing. And RISC type of thing is not suitable because they have more of computation intensive operations, not memory intensive, or the data that they need to handle is much lower than what the graphics processing units have to handle. So this is the major difference between a normal CPU, which is RISC based, and a GPU, which is a different architecture. Now coming back to the memory hierarchy, as I mentioned, registers are very close. The normal way of doing things is smaller memories are faster and expensive. Okay, whenever you want to have memories which are very fast in terms of access time, they are very expensive in terms of every bit of memory needs more cost to be spent. Okay, and they normally they consume more power also. They consume more power, it costs more per bit, and it is faster. Whereas slower memories, they are cheaper, they consume less power, and they are larger in size. Normally, these larger memories are kept away from the CPU, and the smaller and faster memories are kept closer to the CPU. That is the memory hierarchy. The capacity keeps increasing as the memory goes away from the CPU. Performance keeps improving in terms of access time, in terms of faster access. Performance keeps improving as the memory comes closer to the CPU. So we use different technologies for different levels of memories so that they match the requirement of our this hierarchy. Okay. Now, how does it help us in achieving the performance goals? Okay. Let us see that. The main reason for still accessing the memory which is very close to the memories are very fast. Okay. The memory which are closer to the CPUs are very fast in terms of access, whereas the farther one memories are very slow, but size is more. But how does it gain? How do we gain in terms of performance? That's the question. The main reason for why we are able to perform well in terms of executing the program is because of the inherent nature of locality of reference with our software. Now, let me explain that locality of reference. Okay, there is some problem with my mouse. Okay, let me discard and open it again. Okay, okay, there is some problem. Fine. Now, reuse of nearness in accesses. That means when you have software, when you write some arrays of memory, we always tend to access the nearby locations. Okay, that is the spatial locality. Okay, space in terms of space. We normally operate on a particular array which are in the same area. Okay, very close areas. Locality of reference, that's what I'm saying. We are reusing the nearness accesses, okay, most of the time. Another one is for loop. When you have for loop, the code which is written inside a for loop is going to be accessed multiple times. That means not only data which we are accessing that more often, which are closer in nature, even the code area, the for loop, whatever you write, the code is in the code area, which is also accessed quite often in terms of time, temporal locality. Okay, it is also spatial locality because we are accessing the same piece of code multiple times and multiple iterations. On multiple iterations means temporal locality. So if you look at the program, it shows lots of locality of reference. The program tends to access the data which is closer nearby area, and the program which is being executed is also which are placed in the nearby area. So this really made people to think, okay, to make use of these differences to our advantage. We know that faster and expensive memories are normally we can keep it smaller so that these area memories are all smaller in size. The width, signifies that they are the relative size of each of them, and we can keep a larger size here and bring in whatever data we need, whatever code we need. That's why data cache is there and code cache is there, and then operate so often very fast. Why? CPUs are going to access more often this particular data only or this code only more often. So we get a benefit of the faster access. At the same time, the limitation of having very less space is also taken care of because we don't need the complete program for us to run. We need a small portion of the program code and a small portion of the data at a time we need to execute. So we can always bring whenever we need another set of data into the memory and start executing it. That's how the page fault, the paging, all those things were all developed only based on this particular concept of program. Okay, software and hardware, they are very, they work hand in hand and one take advantage of the other. So results in most accesses using smaller and faster memories, okay, along with larger memory available which costs cheaper. So we also need a larger memory because our databases are huge. We need larger memory to store them, but not all the data which is being operated is going to be accessed simultaneously. So we can bring chunks of data into the CPU through caches and we can operate on. So that is the basic fundamental logic behind having memory hierarchy. I hope this is clear to you. I'm sure you might have studied in your computer organization course, but I thought I would reinstate that because it is very, very much relevant for our GPUs and AI chips. Now, 3 properties of memory levels. Okay, that is very, very important. You should know. Inclusion. That means any data or which are part of lower level. So when I say lower level, this is lower level, okay, which is closer to the CPU. Any part of the data which is here has to be present in the higher level. That means that should be here also. And that should also be here. Okay. So what I mean by that, suppose if you are accessing a code which is in that disk. Okay. If you are bringing it into the CPU through caches. Suppose let me call it as L1 cache, let me call it as L2 cache. You need a part of code for the CPU to execute. They will be residing in the code cache of instruction cache of the processor. So what happens is a bigger chunk of that code around that area is brought into L2 cache, and within that portion a small portion is brought into L1 cache, and that is getting accessed by the CPU. Which is accessing it? The program counter is putting out the code instruction address which is getting accessed. Now whenever the PC is accessing, suppose you have a for loop, that part of the code which is part of the for loop must be, most probably it will be in L1 cache. So if you are executing this for loop, when the PC program counter is incrementing and then start going around the loop, they will find out that code is available in the instruction cache, which is in L1 cache itself, which is much faster than going to L2 cache or to the memory or to the disk. So you get a much better performance. That's why inclusion is important. And why is it included? Because you cannot bring any code or data directly to this level I without going through the multiple levels lower. So it has to be filled in L2 cache, then on L1 cache, then comes to the register. So nothing can just jump with crossing the levels. Okay. So inclusion property is important. Coherence. Now what is coherence? Suppose if I have a data which is here, I updated it. CPU is updating it. It has incremented some I++, it has done. Now, as I told you, there is a copy of the same I available here, and same I is also in the DRAM, which is nothing but a main memory. It is also copy is there. So these multiple copies, whichever is having this value I, they should all be coherent. That means if the CPU has modified this value, that should be reflected here and it should also be reflected here. Otherwise, what will happen? Suppose your process goes out of CPU, they get swapped out, okay, by the OS. When it comes in again, you will not see this is out, and then when it is swapped in, you will not see the value which you have updated, which is in the cache here, if it is not reflected in the main memory. So that should be taken care of. Some hardware will take care of that when you have higher multiple levels of memory and they all have multiple copies of the same data or the code. In terms of code, you don't need to worry about because code is not modified, whereas data can be modified because it's read-write. So whenever data is there in multiple places, they need to be updated so that they are coherent in multiple levels. So this is very important. We should remember. And locality of reference, I mentioned temporal reference, which is what is being accessed right now is going to be likely to be accessed in the near future, which is both in terms of code as well as in for loop, as well as in for array accesses. They fall under this temporal locality of reference. Spatial locality of reference is again a piece of code or a data which is nearby. They are going to be likely to be accessed, which are placed very close to together in memory. I hope this is clear to you. Sequential is execution of instructions are sequential in nature, so they will be also a locality of reference. Remember these three properties, why memory levels work, and if they need to work, what properties need to be taken care of. So this is a very important computer science philosophy which all of you should be aware. Okay, now just to summarize, you know registers are there. SRAM, I said that cache is always built using SRAM, static RAM. Dynamic RAMs are for main memory, then hard disk, and then even remote server in the network. So you can see that which is very likely to be accessed by CPU very often. All these things are all seen. Okay. You have smaller, faster, and costlier storage devices as they come closer to the CPU. You have larger, slower, and cheaper per byte storage devices as they go away from the CPU. So this is the logic behind memory hierarchy. Fine. Now I am going to test you whether you understand it or not. So I cannot ask you individually like in class. So what I want you to do is do a self check of yourself. Take a piece of paper, notebook, and try to guess what is the comparison of these properties. Okay. Let me explain. I is closer to the processor and than I plus 1. Okay. As I showed you, I is closer to CPU, I plus 1 is level which is away from the CPU. Now, unit of bandwidth. What I mean by bandwidth is bytes per second. How fast the memory is feeding the data to the higher level. Okay. Or see, always memory flow can happen from any layer to layer, but it could be from here or here. Okay. You can assume that, okay, memory data is coming in. How fast this memory is feeding this data, how fast this is feeding the data, that is called bandwidth. Okay. I want you to compare all these things. Access time, how much time does it take for the CPU to get a data when it wants from a particular level? Okay, whether CPU will get it from I faster than I plus, or which one will it get faster. So you need to compare I, which is closer to CPU, compared to I plus 1. The time, this is in terms of time, which is much faster in terms of access time. You have to say whether it is less than or greater than. You have to choose between this. So I will keep quiet for some time. Please write down less than, equal, less than or greater than for all of this. Okay, I hope you have done by now. So let us look at it. Access time. I said that faster memory is closer to CPU compared to other memory which are away from the CPU. Faster means access time is faster. So T means in terms of time. So which takes less time, where the level which is closer to CPU will take less time compared to the level which is more, because access time is faster in the sense it should be smaller, the time taken. This is microsecond, maybe this is millisecond. Okay, this is faster. Okay, so access time is Ta should be lower for the I to be faster. So you can guess now whether it is going to be less or greater. It is less than. Okay. Now cost per byte. I also said that this is expensive, the memory here, and this is cheaper. So cost per byte will be, Ci will be more, right? So this is the relationship. Memory size. You can see that the width of the pyramid itself shows that the size of each level. So normally hard disk is in terabyte compared to cache which is in kilobyte, right? So you know that memory size Si will be smaller than Si plus 1. Transfer bandwidth. How fast or how much bytes per second, okay, it delivers. Okay. So you can access it faster here compared to hard disk. Okay, hard disk will take more time for getting a block of data to the CPU, right? So the transfer bandwidth is greater for the lower levels, in the sense which are closer to CPU compared to which are away from the CPU. Unit of transfer. So how much of data that you transfer in this level compared to the some level here. See, I can give one good example. When you are shipping something, suppose DHL is shipping some items from India to, okay, maybe US. Now what they do, whenever there is a huge suppose from Bombay they go to India, USA, here they will carry more data and then more amount of items, and then when they go to interstate the amount will reduce because they are going to distribute it, and then within a city it will be much smaller, right? So when you are away from the destination, that is CPU is here and you have a hard disk here, you always tend to bring more data from the hard disk than what you carry from cache to the one level to the other level. So when it is away, you want to get more, suppose things to carry. So unit of transfer, as you go away from the level, it is much more, right? That's why unit of transfer, the amount of bytes you carry is more when the level is here. Okay. Frequency of access. CPU will access more often the level which is closer to it than the which is away from it. So naturally Fi is more than this. Okay. I hope this is clear to you. This is very, very important to understand the memory hierarchy. This comparison will give you a clear idea of why we need it, how we achieve it, I hope this is clear to you. Okay, so this is the logical conclusion of a topic. So let me see whether anything is there. Very good. I don't know whether your answers are right. Okay, I can check. Okay, you might have verified it yourself. Okay, no problem. You guys can verify it. Good. I am happy that you guys are answering here. In CPU, in case if you don't follow any of this, please stop me. Okay. In CPU with GPU system, let me answer this first. Is there a single accumulator or two accumulators since GPU is there? Okay, that's a very good point which I am going to cover. GPU architecture itself is different, and I am going to talk about it soon. Unit of transfer again. Okay, good. So let me open it here. Say unit of transfer means how much you carry when you are having a transfer from one level to other level. Let me explain. Okay, suppose I say told you L1 cache. Okay, L1 cache, L2 cache, and then main memory. Okay, and then hard disk. Okay, different levels. You know which level is what. If you urge you to look at some CPU, okay, some ARM CPU or any Intel CPU, you try to look for block size, okay, block size of caches. Normally, you will see that 64 byte or 32 byte is the block size here, okay, bytes. Whereas L2 cache is 128 bytes or 256 bytes is the cache size at the L2 level. And you know that in main memory, the page sizes are 4 kilobyte or 8 kilobyte, right? Whereas in hard disk, what happens is there have a sectors and then blocks. Normally, 8 kilobyte or 16 kilobyte block size is what is used for hard disk. Why is the size increasing? The block size is increasing. First of all, what does the block size mean? Let me tell you. Suppose CPU is trying to access one data element I. Some data element is there I, which is an integer, assume it is only a 32-bit value. Okay. Suppose that I value is here somewhere in the memory here. Unfortunately, that has not been accessed earlier. Then it won't be found L1 in L1 cache or it won't be found in L2 cache. Now what happens when the CPU is trying to access I, there will be a cache miss. Okay, cache miss. There is not a cache hit. It is not a cache hit. It is a cache miss. That means what? The CPU is looking for the data which is not in L1 cache. Now what happens that time? The hardware looks for the same in the L2 cache because L2 cache block size is bigger. So out of that 128, maybe some 64 bytes or 32 bytes is brought here. So some I may be lying here, which has been brought earlier. Assume that it looks for that in L2 cache and doesn't find it. Then it has to look for whether that particular I is there in the page which is in the main memory. Sometimes even that may not happen. Okay, I am showing it like as if it is there. Suppose if it is not there, what happens? Then OS comes into play. It gives a page fault. Okay. Now what has caused the page fault? The CPU accessing one particular data, some instruction, it said add, okay, or move. It was trying to move some R1, R2. Okay. R2 is the register which is having the address of the I, and it is trying to access that and put it into R1, maybe for doing a arithmetic operation. But this address is not there. This content of that address is not there anywhere, even in the page. Then OS will say notify because it is trying to access something which is not in the main memory. So page fault will happen. This is called demand paging. And then that particular data element segment which is there in the hard disk of the same executable program is brought into the main memory. Now this I has come there now. It is not enough. As I told you, inclusion is required. That means you cannot bring this I directly to the register. You need to fall through all this path. So what happens is from here 128, suppose this L2 cache is a block of 128 bytes. Remember one thing, cache always brings whole block of data. It doesn't bring one byte in the block. Even if you need a one byte, you need to bring whole block into the L2 cache. So this I may be belonging to one level of 128 bytes of data, which is brought into the L2 cache. Okay, I am assuming that cache block is 128 bytes. Now it has come into the L2 cache. So 128 is the size. And then from here, it will not bring all 128 because the cache size is only 32 byte or for 64 bytes. So it will bring, maybe I'll assume 64 byte. This 64 byte in this 128 byte where I is, okay, I will be there in one of the places, that will be brought into L1 cache, and then the CPU will start executing the instruction because it is available. It will fetch from there and start executing it. So the unit of transfer mean what is getting transferred here. It is 128 in as far as L2 is concerned. It is 4 kilobyte as far as from hard disk is concerned, and 64 byte as far as L1 is concerned. So unit of transfer, as it goes away from the CPU, it is much more than what is being transferred here. That's why unit of transfer is like this. Is it clear? I hope my explanation is better understood by everyone. Okay, fine. So let us proceed. What is the time? Okay, we have already crossed half limit. I hope this is very clear to you. This is very important for all of you, whether you are into embedded side or software. You should know this. I hope this is very clear to you. Now let us come into AI with this GPU. Why we need GPU? Now I am going to answer some questions that came up in the chat. So let us talk about multi-core CPUs now. When you have multiple cores, normally each core has its own dedicated L2 cache and L1 cache and CPU. Normally, nowadays, CPUs also have multi-threading. Okay, Intel has hyper-threading. Okay, hyper-threading is a technique wherein each processor, each CPU, this is one CPU, has multiple hardware threads running. That means this is one core, this is another core. Once I say core, it has got its own registers. Okay, all the register sets are there. All R1 to R32, R0 to R32, R31 are there, or maybe more. So sorry, this is CPU. Okay, this CPU has all the registers and they have dedicated L1 cache, but they share common L2 cache. Okay, this is different architectures, but you can assume that this is how I am showing you. Then what happens is the program which is running by the CPU, where is it, my pin? The CPU is executing two threads simultaneously. Okay, that is what is called process and threads. Okay, processes have multiple threads running in them. So when the CPU support this kind of a multi-threading facilities, each thread can run on each CPU. So what happens? This is one set of instructions which is being executed, and another set of instructions are getting executed here. If they happen to be nearby, suppose this is executing one function and this CPU is executing another function, both of them may be in the memory also close by. Okay, so both would have come through the thing. This program is sitting here, this function is sitting here in the L2 cache, F1 is sitting here, F1 is getting executed here. So F1 would have been copied here, F2 would have been copied here. So the function F1 is getting executed here, F2 is executed by this thread here. So you can see the advantage of having nearby program or data between two threads. Then they can use the common L2 cache without having too much of cache miss and hits happening here. Okay, maybe this CPU will occupy this part of the cache, this maybe it will occupy some part of the cache lines. So both will operate without any problem. And when the program goes out of the context, then what happens? This will be flushed and new data will be brought in, and that will be brought into L2 and they will be executing it. So this is how it works. Now there is a problem when you have multi-core processors wherein they are all executing multiple threads. Suppose this is T1, T2, T3, T4. They are all same process. Okay, they all fall under the same process. Then what happens is some data which is getting changed by T2 here may be needed by this thread T4 here, okay, same data, then you may have the same data I in both the places. It is possible, okay. Don't think that they need not have to be in one, no, two places. It can be in two multiple caches and on multiple cores. So when the same data is available on multiple cores on different caches, we need to have a cache coherency. This is called cache coherency. When multiple caches in the cores have the same data, they need to be coherent. Suppose this CPU is updating it and made it to 2, that value should also be reflected here before this core reads that value. Otherwise, there will be a mismatch or there will be a missing of the data updation happening. So that is what is called cache coherence, which will be very prominent when you have multi-core processors which are operating on the same data. Okay, so if you understand this, then you will know what cache coherence means. Okay, I can go on for hours, but we are not teaching architecture here, so I have to little bit go faster. But you can ask me questions offline or online, then I can answer that in the next question or in the lab session. Okay, so understand this at the higher level. Okay, now to answer your question, GPUs and CPUs. See, normally CPUs have number of ALUs are less, okay, compared to the number of ALUs that you see in GPUs. But if you see the size of each chip, the size are same, okay. I am showing the same technology chip, okay. You have to compromise on something to get something more, okay. So it is not that you get anything free of free lunch. So normally what happens is the ALUs which are used by CPUs are more powerful, more features, they can do many operations. Okay, why CPUs are meant for general purpose. Okay, it's called general purpose processors, right? So they are not meant for a particular operation. They are supposed to do integer arithmetic, mul and add, okay, maybe floating point arithmetic, and then memory operations they need to do. They may have to do string operations, okay, string operations also they may have to do, floating point 32-bit as well as 64-bit as well as 16-bit they need to do. So CPUs are meant for general purpose and they have to cater for everything under the sun. So ALUs become huge in terms of size, in terms of logic. So you cannot have more number of ALUs of CPU type in a CPU processor. And control also is complex because it has to manage many instructions, okay, hundreds of instructions they have to manage. That means the control logic is also very large in terms of digital design. That's why the size shown here is much huge compared to what you see here in GPUs, because you are spending less footprint in control as well as in terms of cache, because mostly DRAM is directly connected or they have some mechanism to access it directly. Okay, the cache is little lower and in size, okay, in terms of what you see in CPUs, and instruction cache also is very large in terms of CPU compared to GPUs. Okay, I will bring in one more thing. So because of this difference in the way they operate, and the GPUs are meant for a specific set of instructions. It's not meant for any generic instruction. It's only for matrix multiplications, operations, additions. They are all meant for a specific set of instructions, so they can be smaller in size. So you can accommodate more ALUs in the GPU. So compared to CPUs, GPUs have more ALUs because of this reason. Okay. Now let me explain some more. This is very critical. You should know that GPUs are SIMD in nature. What I mean by SIMD, single instruction, multiple data. That means most of the time, if you see a matrix multiplication, okay, this row is multiplied with this column and then individual elements are multiplied and they are added and the result is put here. Okay, now this multiplication and addition is same mul and add. Okay, this is called MAC operation, multiply and accumulate. So you have to multiply it and accumulate it because you have to add also, right? Multiplied elements have to be added. So mostly the GPUs do matrix multiplication. because even the graphics processing is nothing but matrix multiplication, translation, transformation, rotation, everything is matrix in graphics. If you have gone through computer graphics course, you will know that they are matrix. AI is also all matrix. You may by now you might have studied now. So GPUs gel well for this kind of applications, and they need to do only a simple one kind of arithmetic. And if all of them are floating point, another one thing you know that in AI also all the elements are of the same type, either floating point 32 or 16 or 64, whatever. So they are all of same type, whereas CPUs may have both floating point as well as integer. Here also integers are there for memory manipulation, but mostly the floating point operations for data manipulation. Okay, only address manipulation is integers in graphics, okay, normally. So that is the advantage, that ALUs can be of smaller size and they perform similar operations, and they do similar instructions they do on multiple data, because they do the same multiplication on multiple data. That is why it's called single instruction multiple data stream. Okay, there is a taxonomy. Okay, if you are interested in architecture, Flynn taxonomy, you can Google for this, or I can also share that paper. Flynn's taxonomy talks about SIMD, MIMD. Okay, there are different categories. 4 categories are there. You can read them to know more about this. Okay. So in GPU, same processing is to be done on large volumes of data. So millions of vertices need to be transformed in the same way. So GPUs normally has many number of ALUs capable of performing various floating point matrix arithmetic compared to CPU. So that is a major difference between CPUs and GPUs. I hope this is clear. Here latency has to be as smaller as possible because they are control applications. Here you want more amount of images to be processed, so throughput has to be higher in terms of in the GPU. The performance goals are different. So I'm sorry, let me sorry. Okay, let me see whether any questions are there in between before I go further. Okay, fine. So why GPUs for AI? Now I'm coming to the point. AI processing, mostly matrix computations, need SIMD implementation, which the GPU designs are based on. Okay, as I explained to you, GPUs have huge memory closer to the processing elements compared to CPUs. Okay, we bring in memory closer to the GPUs. How I'll tell you. GPUs have a very high memory bandwidth. Normally, the GPU architecture is designed such that the memory to the ALU interactions are much faster. They bring in lots of matrix, kind of a crossbar architecture, wherein memory can be accessed much faster, not like normal memory hierarchy I showed you. Okay, the CPUs follow that, whereas GPUs follow a different methodology, and they have much higher bandwidth. So since AI operations, including DNN training, inference processing, involve huge amount of data transfers to be performed, which GPUs are well suited for. So GPUs have very high bandwidth, memory bandwidth capabilities. They are designed like that. So it is suitable for AI. But there is still the latency that must hurt performance. They may hurt. Okay, latency is also important. I'm not ruling out that GPUs can be slow, especially edge processing, AI edge CPU process, GPUs, where you have AI on the edges, they need to be much faster in terms of responding to real-time events, like cameras on the edge devices. Okay, so to make them very highly responsive, we bring in processing in memory technique in AI. That means, okay, I told you that RISC processors do not support processing inside memory, right? This GPUs rule out that possibility also. They allow processing in memory. That means I am allowed to do some arithmetic operation or something directly by keeping the data in the memory. Okay, that's how I increase the bandwidth. At the same time, I also reduce the amount of transfer that is required between the memory and the CPU or GPU in our case. So we perform processing in memory. Okay, by keeping it in the memory itself, do a performance, processing. The processing in the sense, perform arithmetic operations or something. Okay, I will not go in detail into that. I will share some paper with you. Interested people can read it. So PIM provides a viable path to eliminate unnecessary data movement by bringing part or all the computation into memory. Okay, you bring either part of the computation, okay, or all the computation into the memory, so that you avoid too much of data transfer happening between memory and the GPUs. Okay, so to summarize, GPUs have more ALUs, so it can help in AI processing. They are assembly in nature, so matrix multiplication and other operations are much easier to perform in GPUs. They have a very high bandwidth, memory bandwidth in nature compared to CPUs, so you can have much faster access to memory, and which are very close to the GPUs. And number of units in the GPUs are also more, so you can perform more operations in parallel, which is very much required for DNN kind of operation. And on top it all, processing in memory helps you in terms of even avoiding the transfer of memory data between memory and GPU. So you better get a much better performance in GPUs. That's why we modify the GPU algorithm to suit it for AI applications. Okay, AI application by nature have huge data. They need SAMD kind of nature. So you can answer all these questions why GPUs are used in AI. No, if you explain all this, I'm pretty sure your interviewer will be very happy, and maybe they may ask you some deeper question which you should have answer, or you can say that no, I am not aware. I'm reading up about architecture more, something like that. You can escape from, but try to be careful so that you don't lead the interviewer into uncomfortable area. Try to read up more about this so that you have a better handle on how to support your statement. Okay, I hope this is clear. Now, let me see whether time is there, and then any questions are there. Okay, already we are nearing. Okay, good. Block size of HD is always greater than the block size of RAM or cache. What is HD? Are you high definition? Are you talking about, or HDD? Okay. Yeah, you are right. Block size is always higher. See, let me explain. Hard disk design is mostly dependent on the hard disk manufacturer. Okay, how they divide the blocks, and then even SSD, the solid state devices or SD card, whatever, they bring in a different kind of scenario now, because there is no latency in terms of accessing the hard disk. Okay, hard disk only is rotating. You need to keep the reader head on top of the platter before accessing it. So all those things are there, whereas SSD doesn't have any moving parts. You can access any part of the SSD memory very easily. So the hard disk access and SSD access is totally different in terms of the way they are structured. But block size is normally much higher. I'm telling you why. Because you need to schedule let us take the HDD example. You need to schedule the read head on top of the particular platter, and then on a particular sector or then access the hard disk. So it will be much expensive in terms of time taken to access the hard disk is much higher. So you need to be, when you position the read head on the platter, it is advantageous to access more amount of data from the hard disk than just reading few bytes from it. Okay, so normally it is in terms of kilobytes. Certainly it is in kilobytes. It depends on the hard disk design. Maybe 8 kilobyte or 16 kilobyte is normally which is being followed. Okay, but which is much higher than the page sizes in the main memory, which is 4 kilobyte or 8 kilobyte. The Linux supports either default 4 or 8 kilobyte. So naturally it is better to bring. Now the problem is one more thing, they need to be mapped to the hard disk, because when you read the hard disk, where do you bring it? You bring it to the main memory. So they should be mapped. Okay, the hard disk block size and the memory page size is normally equal. Okay, it's not more, I would say more, because where do you keep it? Normally what happens is there is a buffer cache maintained. If you read Linux buffer cache, wherein what you bring from the hard disk is brought into buffer cache before getting into the main memory. For the buffer cache is also main memory, but it is meant for hard disk. Okay, see, one more thing I will tell you. Whenever you are writing, okay, suppose main memory, some data is there, you are writing into file write, file IO write you are doing, all that what you write is not reflected onto the hard disk immediately. They are kept in the buffer cache for later writing into the hard disk. Okay, it is written, delayed writing is done. So that's why sometimes Linux takes advantage of this. When you are accessing the file block and you are after some time you are accessing again, even though if it is in main memory, it is not in the page block. If it is in the buffer cache, they bring it from there. Okay, because if it is not written into the hard disk, it is there, the copy is already there, so they bring it back. If you remember, flush is something which you need to do, so that things will be flushed out of main memory to the hard disk. Otherwise it will be still be main memory. That's why when power shutdown happens, sometimes you lose some data because it is not written into the hard disk immediately. Okay, it is delayed. Always don't assume that when you do file IO write, it is not immediately reflected on the hard disk, it is delayed. Okay, so to answer your question, the block size and the memory main size are normally equal. Sometimes it may be more. Okay.